Okay, we've obtained the stopping distance v squared over 12 by multiplying average velocity v over 2 by the time required to stop at velocity v, which is 1/6 v. So that's the distance, 1/12 v squared. That's from the time you hit the brakes until you stop. Okay, now it also takes you a little bit of time to hit the brakes, so there's a little bit, another wrinkle to this model. This isn't an accurate model of how long it takes you to stop from the time you realize you have to stop. And of course that's a very relevant thing to consider. If something happens some distance ahead on the road, then you hopefully stop between the time you become aware of the problem and that's going to involve traveling for that half-second, reaction time of a half-second before you hit the brakes. So the question is, how far do you travel in a half a second at velocity v? You should pause and answer that question, but I'm going to go ahead and answer it now, and hopefully you have done so. Well, you multiply the speed times the time. Time is 1/2 second, so distance is v times 1/2 second, and that's 1/2 v if v is in meters per second, time in seconds. So now, what's the function for your total stopping distance? You should pause while I'm writing this out and write down your response to this. But I'm going to go ahead now and say that the total stopping distance is going to be this 1/2 v that you travel. Distance 1/2 v that you travel before you get to the brakes, and the v squared over 12, the time or the distance you travel after you've hit the brakes. So total distance is 1/2 v plus 1/12 v squared. So now we have this function, which I'll call d of v, which is 1/2 v plus 1/12 v squared. Looking back just a little bit, let me just move this board here temporarily. Okay. If you look at this graph, what we're doing to get the stopping distance after you hit the brakes is we're multiplying this, the value of this function by the average of your velocity. Now, v over 2, if you got speed v, then what's v over 2? You could graph the speed on this same graph, and what you're doing is you're basically multiplying the two graphs in a way similar to what we did with the revenue function. We're multiplying in the revenue function, multiplying the number sold, which is one of the quantities on the graph, by the selling price, which is another quantity on the graph. Not sure that completely made sense, but I don't want to take up any more of your time to digress on that. So if you understand that, great. If not, we can still proceed. Okay, so we have this distance function. Okay, well, what can we determine about this function? You should stop and make a list of the things we could find about this function and how we would analyze this function. We have standard methods for analyzing what kind of a function is this, and how do we analyze that kind of a function. You should pause and think about that, but assuming you have now, This is a quadratic function. The form is AV squared plus BV plus C. And here's zeros. We can get the zeros by factoring. But the zeros are solutions to the equation 1/2 V plus 1/12 V squared equals 0. We can solve this equation by factoring. Or by the quadratic formula. And we can use the quadratic formula for using that to find the axis of symmetry for the graph. We could find the vertex of the graph. We could also find the y-intercept using the techniques, same techniques that we used previously with the demand function. So what we get, and I'm not going to go through the details of that this time, I'm just going to give you the results. Okay? I'll point out, if we factor out a 1/2 V, we end up with V plus 1/6 V squared equals 0. Well, yeah, 1/6 plus, yeah. Again, if we factor out 1/2 V, not sure I said that, we end up with 1 plus 1/6 V, so that our solutions are V equals 0 and V equals -6. If we use the quadratic formula, we'll end up with the same thing. We end up with -1/2 plus or minus the square root of 1/2 squared minus 4/12, which is 1/3, all over 2 times 1/12. I'm saying that you can plug that into the quadratic formula. So that's by factoring. Your quadratic function parameters are A equals 1/12, B equals 1/2, and I think when I did the discriminant a minute ago, I made a mistake. We get C equals 0, and from that you can find what you need to find. The vertex is on the axis of symmetry. X equals V equals -B over 2A, and that's going to be negative of 1/2 over 2 times 1/12, and that equals -3. So if we want to graph the function, it's going to have a 0 here, it's going to have a 0 at -6, on the v-axis. Axis of symmetry is here. And the vertex will be at v equals -3. If we plug in -3, we're going to get 9 here, -3/2 here. We're going to get a negative value, which doesn't correspond to a real velocity. What's that going to be? That's going to be 3/4, and 3/2 is going to give us a vertex at -3/4, and something's wrong with that. Let me pause for a second. Okay, forgive me for the pause, although you probably didn't notice it much, except that I said I was going to pause. I wanted to put -3/4 here, and that didn't quite seem right, so I had to kind of think it through, but that is what we get. Now, that's counterintuitive, which is not what stopped me. I just thought we'd have a bigger number there. That's not really a stopping distance, but then negative speed. Oh, heavens. I just realized that you can't see the board. Okay, let's fix that. Okay, well, again, here's our graph. I still can't see it. Okay, here's our graph of distance d. I have to raise the camera, sorry. Okay, distance d versus velocity v, using your axis of symmetry at v equals -3, and what you can get from your zeros at 0 and -6 velocity. You get these 3 points on the graph. You can see that the graph is going to look something like this. And this intercept here, well, it's not an intercept. The coordinate of the vertex is -3/4, which corresponds to a distance of -3/4 at a velocity of -3, neither of which is real. Your speed is going to be greater than 0. Now, velocity can be less than 0 because velocity has a direction, so you could be going the positive or negative direction, but your speed is simply how fast you're moving regardless of direction. So here's your speed. A negative speed isn't real, but to graph the function, we'd want to find these aspects of the graph. The real world starts here, and the real world is in your first quadrant here. Okay, positive v, and of course all the distances are, none of the distances are negative in that case. So we can get that whole graph and get the complete analysis of this function.